Section 4.2, graphing quadratic functions in vertex, also known as parabolic or intercept form. So we're going to take a look at two other forms that you may or may not be familiar with. Intercept form, probably not familiar with this one. But these forms have their advantages, as does the standard form. They are useful for finding, for example, in the vertex form, thus the name, the vertex form, you can very easily find the coordinate for the vertex. And the intercept form, you can very easily find the x-intercepts for this given parabola. So here is the vertex form. Y equals a times the quantity x minus h squared plus k. And it looks a lot like when we were talking about our review material, and we talked about transforming equations. It looks a lot like the capital A we use to refer to a vertical stretch factor. The H looks a lot like the C that we use to refer to a horizontal translation left and right. And the K looks a lot like the D, capital D, that we used to represent an up-down translation. This vertex form, or a parabolic form, graphs a parabola just as our standard does, so they look like this. So in the blue here, we have our parent function, y equal f, or f of x equal x squared. And then we see, if we add a translation hk in there, or move the vertex, then we get this red graph that's on the right. And what do we pull from the vertex form? Well, we pull the h and k, which again is like our CD translation vector that we talked about last week. And we notice that the values of h and k are the coordinates of our vertex. So we can very easily come up with the vertex. The next thing that we can pull from this is, once you know where your vertex is, remember that in a vertex, the x coordinate of the vertex tells you where your axis of symmetry is. And so we don't have to do really any work to find axis of symmetry or vertex. We can just look at the equation and pull that information off of here. So that's what's happening. And then as a standard form, if we have a positive A, our graph opens up. If we have a negative A, our graph opens down. And remember that if our graph opens up, our vertex is a minimum. If our graph opens down, our vertex is a maximum. So this is our new form that we're going to use and see how it comes in handy for us. A few graphing examples here. We're going to walk through some of these. So our first one, we notice that it doesn't look, this equation A does not look like my ax squared plus bx plus c. Remember, that's our standard form, so let's just make a comparison here. That's the standard form that we were using the previous section to this one. And now we're in this parabolic form. So there's my A, here's my H, and here's my K. All right, so from that, we know that our vertex, which is this coordinate hk, is going to be 3, -5. And we should probably start by plotting that point. So go right 3, down 5, and there's the vertex of this parabola. I know that my A is 1/2, which means it's positive. So my graph is going to open up from here. What is my axis of symmetry? Well, my axis of symmetry, which is this h value, is equal to 3. Remember, the axis of symmetry is a vertical equation, x equals 3. And that's where our vertex is. It's on x equals 3. All right, so what can we do with that? We just have that one point. How do we determine what the rest of them look like? Well, there's a couple different things we could do. When we were in standard form, we found the y-intercept, and then we used reflection to find another point. We could do that here. We can find the y-intercept. And again, we make x equals 0 to find the y-intercept, so we can get y is equal to 1/2, 0 minus 3 squared minus 5. And if we go ahead and follow my order of operations, -3 squared is 9. 1/2 of 9 is 4.5. line or axis of symmetry. It's a mirror, so on the other side of that axis of symmetry will be a point 3 units away from the y-intercept. So move 3 units to the right of the axis of symmetry, and we get that other point there. Now, how do we find other points? Well, we could, like we did when we were just working with tables, now we could just put in, let's say, x equal 2, and then calculate what y would be. Or maybe y or x equal 4, and calculate what y would be. But remember, if you get points other than your vertex, you can always just by reflection find the mirror image. So we could, if we wanted to, kind of do a kind of a simple sketch of our parabola just using those 3 points. But again, I can plug some x values in and find out what y is. So there's that. Now I'm just going to keep rolling through this. So if you feel like you want to practice with one of these equations before you see the answer, you might want to pause the video and then practice it and then turn it back on and see if you're doing all right. I'm going to go ahead and finish B here. So I'm identifying what we have. Axis of symmetry, x equal -1. So we have a -1, -2. There's that mirror line right there. Parabola opens up once more. So let's find that y-intercept. Make x equal 0. And we get y is equal to 2 times 0 plus 1 squared minus 2. 1 squared is 1 times 2 is 2. 2 minus 2 is 0. So at y-intercept of 0, by reflection, I would go 0 or 1 unit to the left of that axis of symmetry, and we get our parabola like so. Then we have C here. We don't really notice an A value. I don't see a number in front of the parentheses, so does that mean there is no A? Well, the A is just -1. H of k, or H and k, is 4 and 1. So don't let this negative affect what you calculate or write as your H value. A negative has some other role, and that is to reflect the graph vertically. All right, so we know we're at 4, 1, and my A is negative. So now what this means is my graph is going to open down. Y-intercept, I think we're going to put ourselves off our graph here, but let's just at least see what it is. So y is equal to -0 minus 4 squared plus 1. So -4 squared is 16, and this negative out in front would make that -16 plus 1 over -15. So I'm going to be off of my graph down on -15, and I can reflect on the other side. So I don't really have a great graph right now to be able to graph this using single units, each square representing 1. So I'm just going to kind of adjust my scale here. I'm going to go, let's say I go by 3s for each square. So 4, 1 is going to be right about there. And then going down, -3, -6, 9, 12, 15. There would be my y-intercept. So I can reflect on the other side of this line here. I'm 4 units away there, so that means I'm going to be 4 units away on the right-hand side. I'm going to be over here at 8, which is right about there. And I get my graph. So you're going to have to be careful when you're scaling your graph differently. There's that graph. So that's the vertex form. Real nice to be able to find axis of symmetry and vertex. Then we get this next one, intercept form. Again, intercept form tells you that you're going to be finding or using the x-intercepts of this parabola. Once again, that A shows up. Now, if we've been at all thinking about our parabolas when we draw them and we have x-intercepts, we'll always, if we're paying attention, we're observing that that vertex is always right in the middle of your x-intercepts. So it always splits the values of my x-intercepts. And so in the vertex form, I can't see the value of the vertex, but I can do some calculations to help me find it. So again, what do I see in the intercept form? Is I do see what the x-intercepts are, these p and q values. And again, we're thinking opposites. So x minus p, if that was an x minus 4, for example, my p would be a positive 4. Axis of symmetry is always halfway. And unlike our standard form with x equal negative e over 2a, now we have this x equal p plus q over 2. P plus q over 2 is an average. It's an average of my two x-intercepts. So that's what I'm going to use to find my axis of symmetry. Once I know my axis of symmetry, to find the y part of my vertex. So this x part of my vertex is really p plus q over 2. And then I plug that value in, and I get to find out what this y value is. So let's try a couple of these. Let's try this one. Intercept form. Well, what's different about this than what we saw up in the example is I only see one parenthesis. So you might be wondering, are there two x-intercepts here? Well, I'm going to rewrite it, and you're going to tell me whether or not I want to know, is that the same thing right there? X minus 4 plus 0 times x minus 4. This is the same thing where I actually notice P, Q, and don't get hung up on the first one having to be P and the second one having to be Q. It's not really a big deal. We're just finding the intercepts. So we're going to go ahead and say, oh, I don't see a parenthesis with that first x right there, so that means one of my x-intercepts is going to be 0. And the q, one of my x-intercepts is going to be a 4. So I would go ahead and on graphing this, I'm going to just go ahead and put those on my graph to start with. And I know that my vertex is going to be right down the middle of those 2 points, so I'm going to have to find the average between them. Oh, that's easy enough. We have our equation p plus q over 2. That's how we find the x part of our vertex, or the axis of symmetry. All right, so x equal 2 is my axis of symmetry. You guys probably already saw that. And then now we go find the vertex. So we find the vertex by plugging a 2 in to my equation for x. Following, here we got negative 2 times a negative 2 is a positive 4. Follow my order of operations. 2 minus 4, negative 2. Negative 2 times negative 2 is 4. And so therefore, my vertex has a coordinate of 2, 4. Well, that means I'm above my x-intercepts here. Is that right? I go back and I look at my original equation, and I notice that I've got a negative out front for my a value, so I'm opening down. So yeah, we're all right. There would be my parabola. All right, what about this next one here? Again, if you want to practice on it and then come back and check the answer in just a second, go ahead and do that. I'm going to go ahead and run through the problem right now, identifying my intercepts. And then from there, finding my axis of symmetry. And then from that, finding the y part of the vertex. We get 2 and negative 2 is negative 4. Negative 4 times 2 is a negative 8. Therefore, my vertex coordinate is 3, negative 8. That vertex is important. I want to always be checking that vertex out. It's going to give me a lot of information, especially when we do our application problems. All right, I'm going to go, and I'm going to go by 2's here. So I'm going to go 3. So I go 1 block, and then half a block over, and then down 2, 4, 6, 8. There's 3, negative 8. I'm going to go find my y-intercept. Why not? Make x equal 0 again. So y would equal 2, 0 minus 1. on the other side. So I have that stretched out graph vertically. We already knew that though. Vertical stretch factor was 2. So I'm vertically stretching out my graph. So my vertex and my intercepts coming up with my values. I'm going to skip this one, and we're going to get to the writing of vertex or intercept form, writing the standard form from vertex or intercept form. And this is where we think about distribution, expanding. So I have in this case, I hope that you're identifying the type of form that you see here. This is in intercept form. Kind of the big giveaway between intercept and vertex form is vertex form has that quantity squared, and intercept form does not. So here we have intercept form, and we're going to write it into standard form, which again, ax squared bx plus c is equal to y. So what we do here is we just simply distribute this stuff. So I like to, I'm going to keep my coefficient out there of 3, and I'm going to work with the x minus 4 times an x plus 6 quantities here, these two binomials. And I get an x squared plus a 2x minus a 24, if I were to go ahead and expand those out. And then distribute that 3, and we are now in standard form. So it's really fairly straightforward. Distributive, expanding, put myself in descending order, highest power first, and then working my way back down to a constant. All right, again, if you're going to check your work here, I'm going to go ahead and do B. You might want to pause and come up with your answer, and then start this up again and see how you did. So we get x squared minus 5x plus 2x minus 3x. That's 2, negative 5, and negative 10. Negative 2x squared plus 6x plus 20. All right, what about going from vertex to standard form? Then we'll get to the, later on in another section, we'll learn how to go from standard form into vertex and intercept, and that's a little more challenging. We use something called completing the square for that. All right, this is really no different, and I mean, essentially what you have here is you have an intercept form, it's just written different. So here I am getting rid of that power of 2 and just writing it as two binomials, it's the same thing that are multiplying together. What's different between this and my intercept form is I got this 25 that's a constant hanging out there. So what do we do different? We really only have to add that 25 at the end. That's the only step that's different. You don't even have to expand out the x plus 8 squared. There is that rule, I don't know if you're familiar with this, but if you're squaring a binomial, you could always do this. You could always come up with an answer by doing squaring the first term. And that would be x times x, so we get x squared. And then twice the product. What that means is you take the x and you multiply it times the 8, and you multiply that times 2 for twice, and you get 16x. And then the last part is square the last. Take the 8 squared, and you get a 64. So what x plus 8 quantity squared is x squared plus 16x plus 64. We use acronyms to do this. We call it the square the first, twice the product, square the last. Again, squaring a binomial, you can use that little trick right there. All right, so I have negative 1/2 times x squared plus 16x plus 64, and then I have this plus 25 that's tagged on at the end. Distribute the negative, negative 1/2 x squared minus 8x minus 32 plus 25. And finally do all my combining like terms, where the negative 32 plus 25 gives me negative 7. And now I'm in standard form from the vertex form. All right, I'm going to actually skip B here. And I want to get to this application real quick and see if we can wrap this thing up with an application. So we have this object that's propelled straight upward from the Earth at an initial velocity of 80 feet per second. Its height after t seconds is given by the function h of t equals negative 16t times t minus 5, where t is the time in seconds after the object is propelled, and h is the object's height in feet. All right, so we get a little visual here of what's happening. We've got some object propelled. Obviously, it's being thrown, kicked, whatever. Not like a rocket where it's got a constant force pushing it through the sky, but just like a thrown object where you release it from your hand and then it's on its own and let gravity take control after that. And so we've got this object, and we've been given some information about velocity. We were given a function that we can use, which is kind of nice here. And we're going to answer these questions. How many seconds after it's propelled the object hit the ground? All right, so what are we looking for? You know, we look for the questions. How many seconds? That's what I'm trying to find. Other information. This is interesting information. We hit the ground. And why that might be interesting, again, a little visual, maybe a little picture. Here's the object to start with. It's propelled up into the air. It comes back down and hits the ground again. All right. We really don't know the height of that object. We only know that it left with a velocity of 80 feet per second. That's it. And then we have this equation. So I would, at this point in time, I'd ask you to kind of stop the video and see if you can come up with some things. What are some assumptions I'm going to make? I don't really have to define my variable that's already been done. But how would you tackle this problem? How are we going to answer the question, how many seconds after it's propelled the object hit the ground? I'm going to keep going, so this is the point where you might want to stop right here and think. We've been working previously with an equation that looks somewhat like this. And that's our projectile motion equation, where v sub o is the initial vertical velocity, h sub o is the initial height of the object. And we've kind of got that thing going on here. The equation just looks different. The equation is in one of our other two forms. So hopefully, you're identifying here, you look at that and you say, oh, I know what that form is. That's, well, in this case, you know that that's intercept form. And so how do I use the intercept form to help me answer this question? How many seconds until it hits the ground? Well, I know that at the ground, which is where it started, I have 0 feet if I'm using this ground level as a datum line. And so if I'm back at the ground at 0 feet, that must mean, again, we're going to use the intercept equation. I know that 0 is equal to negative 16 t times t minus 5. Well, if that's the case, zero product property says set each of those factors equal to 0. And let's go find out what t is. T is equal to 0 seconds. That doesn't make a whole lot of sense. We already know that. But t is equal to 5 seconds. So that's what we're seeing right here. I'm going to put like my time height grid here. Here's my starting point, time 0. I let the time go, I get up to a certain height, and then I come back down. And look at this, 5 seconds later, I'm back onto the ground. So that would be my answer for part A. What about part B? What is the maximum height that this object will reach? Okay, well, we can figure that out, because that happens at the vertex. So if my maximum height occurs at the vertex, and I just found my P and Q's, and I know that my axis of symmetry is my average of my P's and Q's. 0 plus 5 over 2, and I get 2.5. Well, we're talking about seconds. This is really a T. Now that's how long it takes to get to the maximum. So I'm really looking for h of 2.5. Negative 16 times 2.5 this is negative 2.5, and then negative 2.5, and 2.5 is negative 6.25. Negative 6.25 times 16 is negative, I think it's 100, not negative, I think it's 100. So that's the object's maximum height, is 100 feet. All right, there we go. There's a simple application problem, but one that we see often within the context of quadratics. Hope that was helpful.